I can extend it to like Tuesday the week after. Everybody got a fair chance. Okay, but somebody want to get it done by Wednesday week 10, then it's okay. Yeah, but you have to show me something on Wednesday. Yeah, so if your group is on Wednesday, so that is the plan for the next 2 weeks. So we are in week 9 already. So fast approaching the end of the term. So now we just try to discuss about the implicit Runge-Kutta method today, and you got everything you need to do for the project. Yeah. So last week we was talking about explicit Runge-Kutta method, and explicit Runge-Kutta method is generally given in this form. Okay, and now by now, you should be able to get out the formula. Suppose I give you a table, a tableau, then you should be able to write out the explicit formula based on this general formula. Okay, and if you look at the past exam paper, there's a lot of questions like this. So give general formula like this for explicit Runge-Kutta method, then give you a table like this. Yeah, then can you write down the formula to compute yn plus 1? So you have to understand the formula here, and you just plug it in, where to plug in the numbers. So we've done a lot during the tutorials already. Yeah. So now if you look at this, the explicit method, everything can be defined explicitly, right? Because you have xi1, then defined by yn, then xi2, everything is defined by previous known quantities. So this one is xi1, yn, and then xi3 just depends on xi1 and xi2. So previously defined already. So everything explicitly defined. Okay? But, Runge-Kutta method, can allow implicit way to define it. So this one is the 4th order explicit, yeah. But now, so this is an example, yeah. So example we discussed this one already. So now we move on to implicit Runge-Kutta method. So now implicit Runge-Kutta method. Now you can see that you have side j here, okay, on the left, and on the right. Well, this one is explicit, yeah. So everything stops at j minus 1. But for implicit, you have side j on the left, but you have side j on the right as well. Yeah. So then, after that, then you got yn plus 1. So somebody started working on the implicit Runge-Kutta method for the project already, and you saw that problem. You saw xi1 and xi2 appear both on the left and on the right of the system. And so how do you do that? You have to solve a nonlinear system. Okay? So maybe we just give some examples. So now this one is a 2-stage implicit Runge-Kutta method of order 3. Okay? So how do we write out the equation? So now, based on this coefficient, you have xi1, then 1/4 is here, so 1/4 is here, so xi1 here, then minus 1/4, so minus 1/4 is here, okay? And so C1 equals 0, so there's nothing here. C1 equals 2/3, so you have 2/3 here. For the second row, you have xi2, yeah? Then this one is 1/4, so 1/4 is 3/12, it's 1/4, yeah? This one 5/12, so 5/12 is here. Then C1 is 0, so nothing here, and C1 is 2/3, so you got 2h/3 here. Okay? And then you define yn plus 1 just based on those coefficients. B1 here, h/4, and B2 just 3h/4. Okay? So you see, here you got xi1 and xi2 on both the left and the right hand side. Yeah? Then how do you get xi1 and xi2? You have to solve a nonlinear system. And now you can use whatever way, fixed point iteration, Newton method, or the quickest way, just use fsolve inside MATLAB. So fsolve is the built-in MATLAB that allows you to solve a system of nonlinear equations. Okay? But now remember, in your project, yn is a vector, 3 by 1 vectors. Yeah? F is a 3 by 1 vectors. So your xi1 is a 3 by 1 vectors as well. Okay? So actually in your project you don't have 2 equations, but you have how many? 6. Okay? 6 equations, 6 unknowns. So it depends how you arrange it. But you should solve 6 equations at the same time. And that should give you like, xi1 is a vector, xi2 is a vector, and then you just plug it in. Question?
If you use fsolve, but you just feed it all this stuff as vectors, will it still be able to solve for you? Just give you the solution as vectors?
fsolve allows you to solve a system of nonlinear equations, and then it returns a vector. So, you go to MATLAB, yeah? So you help fsolve. So reference for fsolve. So maybe let me blow up the font a bit. So still a bit small, but anyway, you can see that this one is a system. Yeah, maybe make it bigger. Yeah. So, sorry. So you can see that solve two nonlinear system of two nonlinear equations in 2 variables. So you have x1 and x2, right? So first you convert it into the form fx equals 0, yeah? And then you define a function. So the function f is defined like this. So it receives a vector, okay? So vectors has 2 components, and it returns 2 components, okay? F1 and F2. And then you just plug it in. So you have to give a function handle like this, or you just put in, add root 2d inside, and then you solve it. You have to give initial data. So initial point can be 0, 0. So in your case, your initial point could be like a vector 6 by 1 vectors, of 1, 1, 1, 1. Or you can define your initial data to be a 3 by 2 matrix. Either way, but remember that you have 6 unknowns in your project. Okay, so you can rearrange it like x1 up to x6, or you can rearrange it like 2 unknown vectors. It's up to you, okay, but it should work, yeah? So any question about this? So somebody, last year, I saw somebody use fixed point iteration. It still works as well, okay? He just wrote a tiny bit of fixed point iteration solver inside the implicit Runge-Kutta method solver, and it still works. So either ways, okay, now you have a lot of tools already. Should be able to get it done, yeah? So maybe as a practice, let me ask you to fill in the coefficient for implicit Runge-Kutta method of order 4. So this one is in the lecture notes, yeah? So in the lecture notes, you can see that here, the slide here, yeah? So in the next slide, so this one order 3, yeah? But what I need you to do is the order 4. So this one is the implicit Runge-Kutta method of order 4. And you have those question?
Why is it order 4?
Because if you implement correctly, the order of conversion will be h to the 4th. Okay? So if you got your order of conversion is not h to the 4th, then there is something not correct about your implementation. Because I've been using this project for the past 5 years, and everybody if, you know, I mean, they got the correct implementation, they got out of 4. Yeah? And so now let me fill it in the formula. So now suppose I make this one where everyone can edit, yeah? So let's see. Everyone can edit, yeah? So can you edit this one? So what is side 1, side 2 in this case? Can anyone get in this one or no? Access? No, maybe should we edit? Yeah, anyone can edit. Can I make it edit already? Still no one can get in. Maybe the link is not correct. Okay, so let me fix the link. Yeah. So copy. No, I haven't made it visible. Okay, so can you get in now? So can you click on the Google? Sorry, can you click? You go to Moodle, yeah. You click on this implicit Runge-Kutta method. Can you see it now? And can you edit it? Yeah. Okay, so you can edit it, right? So now, okay, so now we need to write down the formula. So this one is the one you need for your project, yeah. So can you write down the formula for this table? So what is your side 1? So write down correctly. Anyone? So what is side 1, what is side 2, and what is yn plus 1? Well, doesn't have to use the fancy fonts, you know, just use side 1. just give like, just type in side 1 like this, and then it will be faster. We don't have a lot of time, yeah? So side 1 equals something, side 2 equals something, yeah? And then yn plus 1 equals something, you know, just make it quick. We have other things to do. It's okay, if you can do it fast. If you can do it fast, just do it. But what I want is, what is the correct equation? So what is the correct equation for side 1 and side 2? Because this equation is exactly the one that you need for your project. Yeah? And you need to solve it. So anyone who has done it should be able to write down. Huh?
Oh, sorry.
This one is the implicit method, implicit Runge-Kutta method. So this table exactly from the lecture notes. So if you write down the formula correctly, then you can solve it. And then that is the part of implicit. Because you see, for the project, there's 3 parts. The Euler method and implicit Runge-Kutta method, everyone can do it. But the implicit part will make a difference within the groups. Okay, some group can get it done quickly. Some group cannot get out of 4, you know, still running, and some group can get up to out of 4, and some group couldn't do it. So make a difference. Right? So Euler method is easy. You know, explicit Runge-Kutta method is easy. Yeah. So I had a sample one-dimensional version already for that on Moodle. So just adapt it to the vector form. But this one will be original contribution from each group. Okay? So everyone should be able to do it once you know the principle. So far so good. A quarter H, yeah, and then, well, you forgot an F. There should be an F here, yeah. So there should be an F. Yeah, okay. So But you got it, okay? So there should be an F somewhere between the, okay? And then Tn plus C1H. I can copy this for you, yeah? So you want this fancy fonts, yeah? Okay, can make it like this. Okay. So far so good, yeah? So this one is the coefficient here, yeah? And then, so anyone start working on this one? So Tn square root 3/6, yeah? H, yes, correct, yeah? So you see, because I don't have this formula explicitly in the lecture notes, so I want a record here. So everyone can have a look at this and make sure that, you know, the equation is correct. Because, say somebody email me, say that, okay, I typed everything exactly, but I got auto conversion only 3. So is there something wrong with the table? Okay? And I say that no, it's not something wrong with your implementation, because the theory in this case has been checked and verified that those coefficients will give you order 4 conversion. Okay? So this one xi2, and then what happened to sorry, this is xi1. What happened to the term xi2? Okay, so this one I will copy this inside and make it look nice. Okay, so make it look like this. Let's see, in MATLAB you cannot define the special symbol like this as a variable. Okay? MATLAB doesn't allow this type of symbols yet to be a variable, so you have to use xi1, xi2, something. So you get, so this term is correct, yeah? So you got like h/4 coming from this coefficient, and then Tn plus, you know, this factor comes from C1, okay? Then xi1, then this factor times h. So I think the second one is okay, yeah? So the second one is, we're going to new line like this, yeah? So the second one, so you got this coefficient come from here, okay? And this one come from here. So this one could be, I can make this one nicer by copy this special symbol. Okay. So this one 1/2. So you see, you see every coefficient has to be used, yeah. So this one is 1/4. This one is Tn xi1. This one is, you see, this f has to be inside. Okay, so this one is the one. So this one is not exactly correct. So this one should be f like this. Okay, so the whole thing here should be multiplied by h. Yeah. So we can use MATLAB notation star for multiply. Yeah. So it's very, very clear. Okay. So you have. So what's going on here? So maybe we split it into a new line. Or maybe make it a new line, yeah, like this. Okay, then Anyway, so you got the idea, right? So this one, those coefficients just come from the table. And this one should be, and this is correct, yeah? So xi1, and the last one, so what happened to the last one? So should be, there should be xi2 here, yeah? Okay, and you should plus the, you should plus this one. So this one is the C2, yeah? Oh, sorry. Yeah, so this one is the formula for the implicit Runge-Kutta method of order 4. And see, on the left you have xi1 and xi2. On the right you have xi1 and xi2 as well. So you need to solve it before you can plug in this. Okay? So that is the implicit Runge-Kutta method. So now we move on. So this one, we just did this one, yeah? So assume that you can write out the formula and then you compute for this. So we skip this, yeah, because this one you have to implement the problem, implement the method, and then you can use that to solve this problem. So now we talk a little bit about the multi-step method. So what is a multi-step method? So let me draw pictures first, yeah. So you should be able to do every step in the project now, yeah, because we just have Euler Runge-Kutta method and implicit Runge-Kutta method. So now the multi-step method. So what is the idea? So the idea is, so if you look at all the methods we have been looking at, yeah. So we just have like this, yeah. Like this. So if we have a connection of dots, yeah. So this one is our Tn, and this is Tn plus 1. Okay, so this is Yn, and this is Yn plus 1. So you see, all the methods we've been looking at, it's just we define Yn plus 1 based on Yn. Yeah, so you just define Yn plus 1 based on Yn. Only one step before the current step, okay? And so that is called this is called single step method. But then what happens if you look further? You know, what happens if you look further, like Yn minus 1? Yeah? Then it will become a multi-step method. So you use those two values to compute the value here. Okay? So that is the idea. So the idea is the multi-step method. So in this case, it's like two-step methods. So at Yn plus 1, you have to look for values at the Yn and the Yn minus 1. Okay? So you have to look 2 steps before the current step you want to evaluate. Yeah? So now there is 2 families of multi-step methods. Okay, so named by the mathematician who invented those methods first, okay, Adams-Basford or Adams-Moulton. And so for the AB method, so what do we do? So you see, first we just write out Yn plus 1 in terms of this exact integral. Okay? then, now what happened is, if you replace, so suppose I have like Tn here, yeah? Then Tn minus 1 here. Then Tn minus 2. And so on up to Tn minus R. Okay? So then, suppose I have the function f that go through, so remember what is the function f? So it's in the ODE y prime equal f, yeah? Okay? So suppose I have polynomials that go through those points. So suppose my function f look like this, yeah? So f is a function of t and y. And now I use polynomials. I use a polynomial that go through those points. So I use polynomials that go through those points. Okay, so this one is my PR. Yeah? So the polynomials interpolate a function f at those points. Okay? And if you remember the interpolation chapter, then you can write your polynomials by Lagrange interpolation. Yeah, so here you interpolate on the point t. Okay, so then you just, write down polynomials, Lagrange polynomial in the variable t. So it will be the form like this. And because I want to label the point based on the Tn, based on the time step, the final time step. So I have PR is just equal this sum. Okay? So remember the Lagrangian. So the Lagrangian is just the product of T minus, everything except the index point. Yeah? So n minus j is the index. So you have I minus j, I different from j. Then n minus I different from n minus j. Okay? And on the bottom, you just have that point, Tn minus j minus everything else. Yeah, so this Lagrangian, so the index looks slightly different from what you've been studying. But it's because we just focus on the last point. So that's why I have the n minus j here, n minus j everywhere here. Okay, but before we just have like 1 to n. But now I just start from n, I go down to n minus r. Then I have this polynomial. So this is my PR. Okay? Then I'm going to replace this integral by the integral of the polynomials. Yeah? So I'm going to replace the integral by the integral of the function by the integral of the polynomials. Okay? So see, before I have yn plus 1. So before yn plus 1 is defined to be this exact integral. Yeah? Right? And now I replace it by PR. So I replace by PR. So this one will become PR. Okay? From, integral from Tn to Tn plus 1. Okay? So what is my PR? So my PR by this definition is just, so this one I replace, so I make an approximation because it's not exact anymore, right? So I got yn plus integral of sum of f Tn minus j yn minus j, right? And L n minus jt from, so this sum from j from 0 to r. So j from 0, then you got Tn and j equal 1, you got Tn minus 1, and so on. So just go backward, okay? And now, you know, because I can exchange the integral with the sum, so then I have the yn plus the sum of, you know, f Tn minus j, yn minus j, the integral from Tn to Tn plus 1, ln minus j. Okay, so j from 0 to r. So that's exactly what I have here. Yeah, so I replace p by f, then the integrals become the integral of pr. Yeah, and then you just put in the formula for PR, then you swap the integral and the sum, then you get this. Okay? And now, you know, this integrals is computable because, remember, ln minus j, you know, just divide by on t and tj. Yeah? And actually, you can compute it by mapping this integral into a standard integral from 0 to 1. Okay? So you make a change of the variable. So here, so maybe let me go back to the previous slide and show you what is ln minus j. Yeah? So this is ln minus j. So this is the definition. So if you put in like ln minus j, it's just the product of t minus t n minus I, then t n minus j, t n minus I different from j, yeah, and I from 1 to r. Sorry, I from 0 to r, yeah. And now if I make a transformation, yeah, so suppose I put s equal t minus tn divided by h. Okay, then what is t? Then t will be, so t will be sh plus tn. Yeah? And then when you plug in this formula, then you have, you know, instead of t, you have sh. So you got L star n minus j s will become sh minus sh plus tn, yeah, minus tn minus I divided by tn minus j minus tn minus I, yeah, the product. I different from j, I from 0 to r. Okay? Sorry, yeah. But, so remember, if we do things like this, so what is your tn in this form? So your tn, so actually before I think we defined tn to be we haven't defined. Okay, so suppose I put tn to be nh. Okay, so then so suppose I define so uniform step size. Yeah, so I got tn is nh. Okay, then what do I have? Then I have this one will be sh plus nh minus n minus ih divided by n minus jh minus n minus ih product, yeah. And you can cancel h, right? So you can cancel h, then you got s minus, well, I mean plus n, then minus n, so it goes away. So s plus I. And then n minus n goes away, so you got I plus j. So the product, so exactly this formula. So sorry, I minus j, yeah? So I from 0 to r and I different from j. Right? So you can make a transformation to convert this ln minus j into this simpler formula. Okay? Assume the uniform step size Tn equal nh. Yeah? So that's how I got this line. Agree? Yeah? And now from here to here, so from here to here, what happened is I just make a simple calculation here. Okay, so now, so you agree that we can get from here to here, yeah? Okay, from this calculation. So how do I get from here to here? So at first I just take this product outside. Okay, so I take this product outside. So it will be a product of s plus I like this over a product of I minus j. Yeah? So this product come outside, yeah? So I still leave it here, unchanged. But what happened to this product? So what is phi I minus j? I different from j and I from 0 to r. So this I minus j I minus j, I different from j, I from 0 to r can be written like this. So I run from 0, so will be 0 minus j, yeah? Then 1 minus j, yeah? Because you run from 0 to r, right? So I just run in. J is fixed. So remember, j is fixed here. And then it will be like 2 minus j, 3 minus j up to r minus j. But there is no j minus j. Because if there's j minus j, then it just equals 0. Right? And you see, because you have a lot of minus here, okay, then I can make it to be minus 1 to the j. Then I flip on the sign here. Yeah, so I got j here and j minus 1, j minus 2, and so on up to j minus r. Yeah? And this is nothing but, you know, I mean, you multiply from j to j minus r, so it's just like you multiply from 1 to j, yeah? You multiply from 1, 2, 3, 4 to j, and you divide it by 1 to j, yeah? So you multiply and divide it by the same thing, yeah? And here you got j minus 1, no, I'm sorry, should be the other way around, yeah? I think should be another way around. So because j minus 1, so essentially this one will be equal minus 1 to the j j factorial r minus j factorial and there must be Is it the correct formula? I think. Anyway, so now, so what we claim is this one will equal this one. So why is the case? So I think this calculation, okay, so let me check it. Okay, but now, you know, I mean, my claim is that this product, okay, 1 over I minus j will simplify to this. Okay, you just expand it out and so suppose we just like believe it is correct, okay? Yeah, so I will make an explicit calculation and post it later, but now assume that's correct. So this one, you just pull it out like this, and then the product of 1 over I minus j will be simplified to this, okay? So it's not very important now, but assume that is correct, yeah? And then I can show you the calculation later. Then we got the AB method. So the AB method, Adam-Basford method, is given by this formula. Okay, and the Bj, so the Bj come from exactly this integral. So, you know, I mean, suppose you have this integral, I mean, L star n minus j equal this, okay? Then this coefficient is just that integral from 0 to 1. Yeah? And you see now depends on R. Then you get a different coefficient. So now let me show you what happened for AB2. So we're supposed to get those coefficients from here, yeah? So what is AB2? So AB2 is when you have R equal 1, yeah? So if R equal 1, then so suppose R equal 1. Okay, then how do I get this? So for R equal 1, then I have yn plus 1 equal yn plus b0 f tn yn, yeah, plus b1 f tn minus 1 yn minus 1, yeah. Okay, so now what is b0? So b0 according to this formula will be given by integral from, so it will be minus 1 to the 0, yeah, over 0 factorials. So R is 1, yeah, so you have 1 minus 0 factorials, and integral from 0 to 1 of, so now this product will be, so s plus 0, yeah, s plus 0 because I from 0, yeah, to s plus 1. Well, I different from j, so there should be no s0, yeah? So there should be no term s plus 0 because j equals 0, so I run from 0 to 1, but it has to be different from 0, so we have only this one, okay? And so this one will be, so 0 to, so this one will be 1, yeah, you have nothing here, and this integral will be s plus 1 square over 2 from 0 to 1, yeah? So this one should give you yeah, so this one should give you 0 plus 1 is 1, 1 square, just 1 half. Okay? No, 1 half and minus so sorry, if I put in 1, then I have 1 plus 1 should be square minus 1 square, okay? So it should be like 4 minus 1 is 3/2, okay? So that's why I got the 3/2 here for this one. Yeah, so you got the 3/2 here for AB2. Okay, and so similarly, you can compute this one. So this one, for B1. So for B1, then you should have, so according to this formula, it should be minus 1 to the 1 over 1 factorial. Then 1 minus 1 factorial is 0. So this one gives you minus 1 only. And integral from 0 to 1 of, now you have s plus I. I is different from j, so j equal 1, so only s plus 0, right? So you got only s, right? And then this one should give you minus 1/2, because they have minus 1 here. So that's why you have a minus 1/2 here. Okay, and so on. So you see this one is when r equal 2. You plug it in this integrals, then you got those magic numbers. Okay, but you see, so what is the difference? So the difference is this method, you look backward only one point, and this one you look backward 2 points, yeah, n minus 1 and n minus 2. Okay, and this one you look backward 3 points, so 1, 2, and 3. Okay, so now, so what is the what is the advantage? So what is the advantage of this method? So we can prove that. So this is a bit involved, but we can prove it by checking the local truncation errors. That if you have r plus 1 step AB methods, then you can have a local truncation order h to r plus 1. Okay. So what does it mean here? So if r equal 3, yeah? If r equal 3, then you have the fourth order. So AB4 here, when you look back, three terms, yeah? Then this one is order 4. So AB4 stands for order 4 methods. You see, so you see by just this formula, this simple formula, it gives you order 4 conversion already. Okay, so compared with Runge-Kutta method, it gives you a lot of, complicated calculation. You have to do a lot of calculation before you obtain the fourth order conversion. But this one is much simpler. But what is the disadvantage? So what is the disadvantage? Now disadvantage is you have to look back, like say this one 4 terms. And you see, when you try to implement it, you cannot start from y1 because y0 is given, right? But you see, if you put y0 here, then it means that n has to start at least 3. Then you have y4. Yeah, so y4 depends on y0, y1, y2, and y3. And so where do you get y0? Y0 is given, but where do you get y1 and y2 and y3? Yeah? Yeah.
S plus 1, and then B1 is all that integral S. Is it because the I not equal to J?
Yeah. I is not equal to J condition, yeah. So that's why you see you have S plus 0 is okay because J now is 1, yeah? But S plus 1 is not okay because you don't have that, yeah? So that's why you have this coefficient, yeah? Okay, so we can show that for Adam-Bastard method, AB2, the local truncation errors is order OS square. Okay, and how do you prove it? So now remember, you just use the Taylor expansion again. Yeah, so Taylor expansion, this one come from, you just expand around